So we are going now to slides 144, 145, and I think that'd be very useful because it brings together a lot of different things that we talked about during the 2 days, IRT and SEM, and measurement invariance, measurement non-invariance. Now when we have, I know some of you have had to leave, and some of you will have to leave soon, but those of you who stay, I think you will benefit from getting a feeling of wrapping things up, consolidating things. Before we go forward, though, well, actually looking way forward, note that not only does Mplus do regular IRT by maximum likelihood 2PL, 2-parameter logistic, it also extends that, as we have alluded to 2-level IRT. So you can do 2-level IRT, you know, of achievement responses of students within schools properly. And you can do IRT mixture modeling, which is a popular new field in IRT. IRT mixture modeling, where a student may use different classes, latent classes of students may use different solution strategies. Different solution strategies. One strategy making being a little bit harder to reach the goal, but feeling natural to one type of person, and another solution strategy having a different difficulty set, but being the preferred way to solve an item for a different class. IRT mixture modeling. And Mplus does not leave any holes unfilled, so IRT with mixture modeling in 2-level settings is also allowed. I think that's chapter 10, multi-level mixtures. So let's go now to CFA with covariates, mimic, and it looks very much the same as with continuous outcomes on the left slide. We're dealing with measurement invariance matters, testing for that, which says non-invariance is the same as bias, item bias, or diff in the categorical outcome world of IRT. And we're interested in population heterogeneity, relationship between covariates and factors, and we are going to focus on the covariate approach. And you remember now from yesterday that there's also the multiple group approach, which is a possibility. We will probably have very little time to do that, given that we have to be out of here in 1 hour. We'll see. Steps in the CFA with covariates are the same as we had for continuous outcomes. Establish a CFA or a EFA CFA model. Add covariates. Check that the factor structure does not change when you add the covariates. And study modification indices for possible direct effects, which are indicators of measurement non-invariance. Add direct effects suggested by the modification indices, and check that the factor structure does not change. And then interpret the model, the factors, the effects of the covariates on the factors, and the effects of the covariates on factor indicators. So same thing as what we did last time, and we're going to use the same data, the ASB data, where now we're going to add some background variables, some covariates. So we're going to take a look at this picture. On slide 148, and that's a mimic model then with 3 factors in this case. And I think that's what we found in our EFA as well. So we're consistent here. Property shoplift, here are the property offense items, 1, 2, 3, 4, 5, 6, 7, 8. It was a little questionable if the one-factor model fit them, but let's stay with that for now. F2, personal offense, fighting, threatening somebody, injuring somebody. F3, drug offense, pot, drug, sold pot, sold drug. And the covariates are gender, ethnicity, and age, measured in 1994. So now, if you look at this picture, then you know that out here in the measurement part of the model, the regressions are for categorical, in this case, dichotomous dependent variables, right? They're dependent variable as a function of the factor. So we use probit or loaded regression. And so these are not linear relationship, but nonlinear relationship. We do not bother to put in the U star variables behind. We could if we wanted to think about it in that way, but we know that that's equivalent to a probit or a loaded regression. So we just draw it like this and keep in mind that these are loaded probit regressions. And then the regressions of the factors on the covariates are standard linear regressions because the factors are continuous variables. So continuous dependent variables give you linear regression even though the dependent variables are latent. So this is a model then that would be what we call the baseline CFA with covariates model yesterday. We do not have any direct effects in here. And we can estimate this model and then look for the evidence of the need to include direct effects to look for measurement non-invariance, which then in the categorical response world, particularly in the IRT connected world, would be called item bias or DIF, differential item functioning. In this situation, I'm again tempted to point out that version 5.1 will be able to do this kind of an analysis with covariates, imposing only an EFA structure over here, an EFA structure, where you don't have to specify these 0 left out arrows that are implied here, but let the program find a suitable rotation of these loadings and have a less strict measurement part here, even including possibly some correlated errors. That kind of EFA SEM, or ESEM, as we call it now, EC SEM, can be done even with categorical items if my indications are correct about what's happening in the programming stream right now. I'm going to go home and test that next week. So in any case, this is an interesting model, and here's how you set it up. It's going to seem so easy now. Use variables are property through a greater than 50, threat through goods, and then you add the covariate sex, black, age. But the only variables you put on the categorical list are the dependent variables, the factor indicators. You don't put the categorical X variables on that list. If you do, you incur the wrath of Mplus. So here's what you say. It's so simple now, right? Model is F, the factor F1 is measured by property through da-da-da. That's an IRT model. And F2 is measured by those items, F3 by those, and F1 through F3 are regressed on the background variables. Very much the same as what we used in the continuous case. Actually, the only difference so far is on the previous slide, categorical R, that statement. And then right away, since we are interested in item bias or DIF, measurement non-invariance, we do include this statement of 0 regression coefficients, property through goods. That's the list of the items on the use variable list. So all of the items, property through goods, all of the items are regressed on all of the covariates X with regression coefficients fixed at 0. So that is the same model as drawn on the left on slide 148. You know, you can include those statements, but fix the slopes to 0. You get the same thing. The only advantage is that this opens up, as Linda said, opens up a matrix which enables you to get the modification indices that we ask for here. And the model results are then you get the factor loadings for each factor. Here you have the loadings for factor 1. So we're looking at, in this case, we did not request we didn't say anything about the estimator, and then we fall into the default estimator, which is printed in the outputs of weighted least squares. So we use weighted least squares here. So these coefficients are the factor loadings in the probit metric, of the probit kind. You could have used ML here as well for these three factors. It wouldn't have been overwhelmingly heavy. And then the default would have been loaded. And here we take the usual factor analytic approach of fixing the first loading to 1 to set the metric of the factor in line with property. We could instead have fixed the residual variance for f. In this case, since you have covariates, it would be the residual variance. And let all of the loadings be free. That would have been possible as well. And given the large sample sizes, all of these parameters are certainly significantly different from 0. F2, healthy, there's not much of a difference between the loadings for the different items, right? They're all pretty similar. Low loadings, tend to go with low reliability. But they're about the same. And then the structural part, leftmost part of the picture, factor 1 on the background variables, factor 2 on the background variables, and factor 3 on the background variables. These are linear regressions. And as compared to, so sex is scored 1 for males and 0 for females, I do believe. Here, boys are bad goes well. So the boys being a male rather than female gives you a higher value on F1, other things being constant. And F1 was the property offense. And you also have ethnicity and age effects. And as a matter of fact, all of the factors are significantly influenced by these covariates. In this large sample, you tend to get significance for everything, almost, not quite. And of course, you can look at standardized solutions, which are out here to the right. We don't have a heading here, but the heading should be estimate here in the first column, standard error in the second, and the z-score ratio of the estimate to standard error, and then STD, standardization with respect to unit factor variance, that is the dependent variable, and then standardization also with respect to the observed variable, which in this case are the x's. So this is STD_YX. And again, you would probably, for a variable like sex, you would not choose the doubly standardized. You don't want to look at the standard deviation change in gender, but instead keep that unstandardized and only standardized with respect to the dependent variable, which is the latent variable standardization in this case, the dependent variable being F1. So that would be the gender effect, 0.653. And then you have an easier time to compare the gender effect on factor 1 with the gender effect on factor 2 and the gender effect on factor 3. They're all significant, but it looks like factor 3, the drug misbehavior is less related to gender than the other two behaviors. It's easy, isn't it? There's nothing new here. We can go home. I mean, it's just like yesterday. And you get a chi-square test of fit, which indicates misfit quite a lot. Even in terms of CFI and TLI. CFI you want to have 0.96 or higher, I think. Chi-square will be too high because you have complex survey here and you'd ignore it. But it would be too high even if you take it into account, I do believe. This low CFI is an indicator that you're not quite there yet. And of course you're not, because we expect to have direct effects. Why do we expect to have direct effects? Because we don't know much about this measurement instrument. It may not be invariant with respect to gender and ethnicity and age at all. It's never been investigated. These items were put together by a committee. No piloting whatsoever. Standard procedure, right? So you're not going to expect a well-fitting model. We're just lucky that the 3 dimensions came out. That was probably a committee decision. But you have no idea how it relates to how it functions in different populations until you do this analysis and look at your modification indices. In early versions of Mplus, we didn't have modification indices for categorical outcomes, but had to work with derivatives. But modification indices now, again, statisticians call it Lagrangian multipliers. All we need to know is that it indicates that if you free a parameter, how much is chi-square expected to drop? And as you will see, when you go through your notes from yesterday and today, those MI indices are pretty darn good at predicting how much chi-square will drop when you free those. If you go back and compare the values, it's a very good approximation. So it's just saying, what would happen if I freed a parameter without having to do that analysis? So it's sort of an extrapolation beyond your analysis. Of course, you could sit and do all of these different analyses, but it would take forever, or at least a long time. So what are the big ones? Well, these are the 2. Phyt on H94. Phyt item sits there on H94, has a direct effect. You also get the expected parameter change out in the output. We haven't given that. You know, phyt on H94 as it stands here is that effect is 0, and then parameter change can be positive, which says that, or negative rather, as you age, you don't tend to get into fighting. We'll talk about the interpretation a little bit more carefully soon. Shoplift on sex seems to be a whopper. So let's focus on only those 2 and see. Con on black, I guess, is another one. So here we have them drawn. Sex onto shoplift direct effect and H94 onto phyt. Let's keep track of those. We're going to focus on shoplift here. So now we've found evidence that there is measurement non-invariance because of a significant direct effect. How do we quantify and understand the importance of that? Well, let's see. This is the input corresponding to the model picture. We have the model we had before, the baseline model, plus the bolded statements, which are the direct effects included per the suggestion of the modification indices. If you want to be a purist, you should just include one at a time and then look at the modification indices again. But with these large modification indices, those 3 are probably still the winners. And lo and behold, CFA TLI goes up a little bit. You get 0.96, at least if you round off, right? But certainly we could include more effects. And, you know, who knows? If the CFA structure is absolutely well-fitting, and if there are, is it really true that you have no residual correlations? So my feeling is that before you get into studying direct effects, you may want to saturate or make this measurement part a little bit more flexible, perhaps through EFA plus some correlated residuals before you start looking for direct effects. So you can see exactly where the misfit comes from. In fact, when I've been doing these analyses on the NIAAA's NESARC data, National Survey Data on Alcohol, I and Tom Harford, we tend to work with EFA and a CFA framework to make the measurement part a little bit less restrictive, to be sure that we pick up the right structural effects here and the right direct effects. But now you can do it automatically. Can you hold it? Good. Yeah, I know it's tempting. Okay, so here we have the results. F by shoplift. Here, what this tries to do on slide 160 is to focus on the measurement non-invariance for shoplift with respect to gender. And Linda pointed out that there were 3 parts to that interpretation. If you remember the picture, which seems like ages ago, we had a little picture with 3 Ys 3 x's, and 1 x had a direct effect. And then we plotted two parallel lines, right, that were not the same, and they were separated, and the separation was the measurement non-invariance in terms of an intercept difference. Here it is in terms of a threshold difference, but it's the same picture. So we want to know how shoplift relates to the factor 1. This coefficient here, it's positive. And we want to know how F1 relates to sex. That's positive significant as well. Males are higher on F1, therefore males are expected to have a higher tendency to shoplift. But shoplift on sex, should really say male here to make it easier, is negative. So how do you interpret that negative direct effect? It's significant. The modification indices were right. It is significant. How do you interpret that? That's what the next couple of pages talk about. The way I look at it, it's quite simple. Shoplift is related to 2 variables, F1 and sex. And what you're interested in, you're not saying that males are less likely to shoplift. Going back to this morning, when you were fresh and everything was hopeful, we talked about marginal probabilities being different than conditional probabilities. A statement like males are less likely to shoplift is a marginal statement. What we want to do here in DIF, in item bias, direct effect measurement non-invariant settings, we want to make a conditional statement. Conditional on F1, how do the genders differ in terms of shoplift probability? So for 2 people, male and female, with the same factor value on property offense, they're just as bad. The male tend to be less likely to exhibit shoplifting. The male exhibits other ways of property offense. That's how you should read it, essentially. And you can do the same reasoning for the other items. And I think that's what the slide 161 says. You focus on effect of gender on shoplift. Direct effect is negative for a given factor value. Given, that's the vertical bar. Conditional on the factor, males have a lower probability of shoplifting than females. Don't say that females are more likely to shoplift. That's another statement. It may not be true. It depends on other parameters in the model. But we have a measurement non-invariance. Shoplifting is not as indicative of a property offense factor value, high factor value, as it is for males and females don't have the same. Shoplifting doesn't say the same thing for males and females about shoplifting, about property offense. In fact, if males engage in shoplifting, that's worse than females do it, is what this model would say. But we don't have to worry about that right now. All we worry about is that item has item bias. It's an interesting question what you do with that fact. It's just like what do you do with cross-loadings, an item loading on more than one factor. It depends. Here, if you, like with cross-loadings, if you do the right modeling, you can keep the item. If you have the direct effect in there, it still can be a good indicator of F1. It just functions differently for males and females. But in some other situations, ETS wouldn't dare to have an item like this. They would throw out the item because it would be an unfair test to one of the 2 genders. But statistically, it is useful to keep it because it informs about F1. You just have to model it correctly. So then you know that this measurement instrument doesn't work the same way for the 2 genders. Which is, that's what you really want to study when you have a measurement instrument. How well does it work in different settings? Here is the parallel lines counterpart in the categorical situation. You've seen this many times. As usual, I don't know how many times we emphasize this now. You try to ignore that linear regression with a dichotomous x1 and continuous x2, but it comes back to haunt you again and again. Here it is, yet one more time. The continuous predictor is F1. The categorical is gender. We plot against the continuous and let two curves be the male and female counterparts. So you say that for the same property of fence value on the factor, you have different probabilities of engaging in shoplifting. And going here, I only went in from the factor. You can go in from the y side here too, except it's a little bit less intuitive since you don't observe continuous values on that shoplift variable. This kind of a graph which shows the item bias. You know, item bias is the difference between these two curves. In fact, old-time item bias computations computed the area between the two curves as a measure of the degree of item bias, differential item functioning. I don't think that's done anymore. This graph can be done in Mplus using the plot command and the option item characteristic curves, where you can condition on a covariate to get two plots and show the item bias directly. Here we have shown how to do that in utter detail, just to show you that there's nothing magic going on here. So you recognize in equation 45 the measurement part of the big structural equation model, U star, the dependent variable behind U, the factor part, and the direct effect part, kappa times x, and the residual. And we're talking about the conditional probability of a U equals 1 admitting to shoplifting response given the factor value eta and the covariate x. Probability U equals 1 given eta and x. That's a probability of being above a certain threshold, right, in the U star, which is 1 minus the probability of being below. And here's then the probit normal distribution function argument. Tau minus lambda eta minus kappa x is what it comes out to be. And then a residual variance, which is not a free parameter to be estimated, but needs to be part of this computation. So here's what it looks like at the bottom here. And an example is given at the end of slide 163. For the shoplift item, the threshold is 0.558, kappa is minus 0.385. That was the direct effect that we saw before. That was shoplift on sex. And if you ask for a standardized solution, you get this theta residual variance printed. Again, it's not a parameter, free parameter to be estimated, but it can be derived as the so-called remainder. So that is the residual variance for the U star variable. And we can compute this for simplicity at eta equals 0, because then this term falls out. Probability is 0.21 for females and 0.08 for males. So at the factor value of 0, this is how big of a increased or decrease in male tendency to shoplift is at eta equals 0. Eta equals 0 is not the mean here, it's just a convenient value that we chose. And even more detail, here's how it was done. So if you want to go through these steps and really know how to compute this, this is what you do. Again, it's done by the plot function, but you know there may be cases for your presentation purposes where you want to make your computations and get the exact values yourself, and it's not hard. You just follow these steps here. It's simple algebra going through using a z-table and nothing more really. So if you want to read applications of this, we have two former Hopkins persons. Lots of this harks back to earlier Hopkins day. Joe Gallo was here, was a postdoc here, and is now at the University of Pennsylvania Medical School. Jim Anthony was here and is now at Michigan State. I was here, and I'm still here. Still kicking. And here is the article I was searching for before. Bob Mislev in 1986 in Journal of Educational Statistics. Recent developments in factor analysis of categorical variables. That's where he compares maximum likelihood EFA for categorical items with weighted least squares EFA for categorical items using my old program ListComp. How many of you have used ListComp? Well, a few years ago, there were some people raising their hands. Yeah, well, Mplus is certainly much more accessible. Here is stuff, a paper that I wrote on this topic that was part of my dissertation, and here is the 89 application in Bill Eaton's special issue. Bill Eaton was just here the other moment before break. The head of the chair of the Department of Mental Hygiene, mental health. More technical paper related to this is Psychometrica paper from 89. Here we did mimic modeling, EFA with covariates in the measurement of attitudes toward career choice in a fellowship for the sociological methodologist Carl Schüssler, which took place, meeting took place at Bad Humbug. Not Bah Humbug, but. All right, folks. We're getting to difficult topics here. And we're not going to say a lot about this topic. Mostly because it follows so nicely from multiple group analysis that we did yesterday. But this is the alternative to using covariates. Same truths hold here for categorical outcomes. The CFA with covariates is a simpler approach than the multiple group analysis. The CFA approach cannot allow as many group differences in parameters as can the multiple group. The covariate approach is better at handling many groups and smaller sample sizes, whereas the multiple group analysis can really break down when you have small numbers, many groups and small and not large numbers of people in the groups. Actually, this paper in Psychometrica has an applied part to it, which goes through examples where you have several groups. Multiple group analysis would be very difficult to do, whereas the factor analysis of covariates is more accessible. It's an interesting paper. This turns out that several things were in there. This multiple group covariate approach to study measurement invariance or non-invariance was in there. The finite mixture idea was in there in an early embryo, and multi-level modeling was in there. It's interesting to see how that, how I was curious about those things even back then. Anyway, in the multiple group analysis, you fit the model separately in each group, and that's what we said before. And then you fit the model in all groups, allowing all parameters to be free except factor means, which are fixed to 0 in all groups. And then the topic of scale factors, which we haven't really dug into, is fixed to 1 in all groups. I'll mention what scale factors are as we get to it. Fit the model in all groups, holding factor loadings and thresholds equal across groups is our standard default option with multiple group analysis. And there you fix the factor means to 0 in the first group, the reference group, and let them be free in the other groups. And fix the scale factors to 1 in the first group and let them be free in the other groups. Add covariates and modify the model. It's the same idea as for continuous outcomes. Somebody asked me, why don't you, as a default, hold every parameter equal across the groups? Every parameter meaning not only the measurement parameters, but also the structural parameters. Good question. If you really believe that that is the model that's closest to the true model per your substantive reasoning, by all means, go ahead and do it that way, and then relax the restrictions one by one. So going from the most restrictive model and relax, sort of backward elimination, whereas this is forward whatever. I would say that whatever path to the best model you can take that is the shortest, that is likely to be the shortest, is the best one. Because the more modifications you do along the way, the more chances you have of modifying into the wrong model. Modification indices, for instance, don't always lead you right. But I have a feeling that measurement invariance of measurement parameters may be more likely to hold than invariance of the structural parameters. So, in different populations, means tend to be different, and at least some of the variances or even the correlations between the factors tend to be different. So hence the default. So measurement non-invariance would be a model with 3 factors here again. Fixing the factor means to 0 in the overall model, which means that they're fixed to 0 everywhere. And then there are 2 groups, males and females. The first group is female, and the second group is male. And we're just saying then that we give male group specific loadings and thresholds. Thresholds coming down here in the brackets, means, intercepts, and thresholds in brackets, and with dollar signs gives it away that it's a categorical item that has 2 categories, 1 threshold. And we let these loadings and thresholds be specific to group male, implying that they are different. These measurement parameters are different across the 2 groups. That's the non-invariant case, which you may or may not want to look at. The measurement invariance case is the default, and therefore it looks particularly simple. Measurement invariance. In the model, you say this. The Mplus sees that it's a multiple group analysis by the grouping equals option up in the variable command, just like yesterday. Multiple group analysis has that grouping equal option. And then in the model command, all you say is this, and that model will have the same measurement parameters in both of the 2 groups, males and females. Partial measurement invariance. Well, you have a model here in the overall, what's common to the 2 groups, and then you have a model male, which says which parameters have different values for males. And here we let the factor loading for con and less than $50 stealing be different between males and females, and the fight item to be different, and sold pot, sold drug would be different. These loadings are different for males and for females, and these intercepts are different for males and females. That's how you allow for, it's not all of the loadings, not all of the thresholds that are different between the genders, but some of them based on our analyses. Let me look. So at that point, I feel compelled to say a few words about the scale factors. You may want to write this down. We don't have an applied slide on scale factors. We have a technical slide on it. But a scale factor is the inverted, the 1 divided by standard deviation of the latent response variables. So a latent response variables inverted 1 divided by standard deviation is the scale factor. Now, why would we talk about variance or residual variances for underlying U star variables when we said that they had variance 1 that had to be fixed to 1 for probit, fixed to pi squared over 3 for logit? Well, when you have multiple groups or multiple time points, you can identify and estimate these residual variances, even with categorical outcomes. If you have a reference group or a reference time point where they are fixed, because it's saying that these residual variances need not be the same across groups or across time. So that's a dense concept, and it's interesting, you don't see it in maximum likelihood modeling of these kind of models. I think it's an oversight because I think the same phenomenon holds there. if you want to read about that, if you're technically interested, there is on the Mplus website these web notes, and web note number 4 describes this in quite a lot of detail. It comes into play when you have partial measurement invariance. I'm going to give you the truly technical description at the end just to blow your fuses, but when you let some items, con, less than 50, fight, sold pot, sold drugs, be different across the items, you can no longer identify the scale factors which you would have otherwise identified in the second group being male. So in that case, we have to fix the scale factors, which are in these, as Linda said, the curly bracket, in these braces. We have to fix them to 1 for those items. And that's what this shows. If you go back one slide here, here are the scale factors mentioned in the overall model, which says that they are fixed at 1 for both groups. They cannot be identified separately from the group-specific factor loadings and thresholds, but they can be identified for the items that are invariant. For the items that are invariant across groups, these scale factors should be allowed to be free, but when you start saying that some items are measurement non-invariant, namely the items that are mentioned here in model male, then you have to go back and fix these scale factors at 1, or else you get a non-identified model. So that's complex and a long story. I, again, want to point you to the literature here. Mplus Web Note 4. It's almost like a paper, but not quite a paper, for those of you technically inclined. And again, the multiple group issues that we talk about here, measurement invariance, non-invariance, carry over to the multiple time point modeling, be it longitudinal factor analysis that I mentioned this morning, bright and early, or be it in growth modeling with multiple indicators, growth modeling with the dependent variable that's latent with multiple indicators, which we'll talk about in August. Here's an early psychometric article, simultaneous factor analysis of dichotomous variables in several groups, from my, I think that was from my dissertation. So that gives you a flavor of what's involved. The Mplus User's Guide gives a clear prescription for how to proceed with the multiple group modeling with categorical items with weighted least squares, probit, which is what we're talking about here, and gives you the specifications that you choose for measurement non-invariance, for full measurement invariance, and for partial measurement invariance. Linda has written out the text for that quite clearly. Since we have a couple more minutes, let's just talk about technical issues for weighted least squares a little bit. And maybe you'll get a flavor of what's going on here. For those of you not technically inclined, now you can snooze a bit and wake up at the very end when we say goodbye. So let's say that we have 2 time points, time point 1 and time point 2. And you have a factor eta 1 at time point 1 and factor eta 2 at time point 2 related to a covariate x. And we take the U star formulation here seriously. We put them in very explicitly, the latent response variable formulation. So this would be an example of a longitudinal factor analysis. It's not multiple group. It's a single group, but it's 2 time points. But all of the measurement invariance, non-invariance reasoning hold true here. So let's put that slide on the left. And on your right, then, some reasoning about that. So for each U, let's start with the second bullet here on slide 174. For each U, and look at the figure on the left, there are 2 U's per time point. The modeling here assumes normality of U star given X. That's the probit assumption. That says the U star given X has to do with the residual variance, what varies when X is constant. I'm asking you, what varies when X is constant? The residual variance for the factor and the residual variance for the U star. So Z1 and epsilon 1 vary. variance of u star given x is lambda squared times variance of z1 plus variance of epsilon. It's fixed at 1, so the residual variance comes out to be the remainder 1 minus this. Now, if you go to the next slide here, say that you consider measurement invariance. I'm trying to take an easy route through the minefield of technicality here. If you look at the figure, let's say that measurement invariance, so the tau 2 is equal to tau 4 and equal to tau. So we're considering the second item, u2 at the 2 time points. u2 at the 2 time points, same items repeated. The variance of u2 given x is this expression at time 1 and this expression at time 2. And that shows that variance of u star given x varies across the two variables if either the residual variance or on the factor or on the u star variable varies, even though lambda is invariant. So therefore, fixing the variance to 1, as we would do in Probit, at both time points would be wrong on the measurement invariance. Because then you would negate the fact that these variances, response variable, residual for the response variables, those variances can change over time as a function of the residual factor variance or the residual variances for the u star variables. So you don't want to force the straitjacket of units fixing a variance at both time points. Instead, you fix it at 1 for the first time point, but estimated for the second. And these deltas are the scale factors. So by letting the scale factor for u4 be free and estimated, the model allows the residual variances to be different and still modeling the u star correlation. So it's interesting, this carries over to standard binary growth modeling, for instance, and you don't see it in the ML world, but it comes very clear as a need for this in the weighted least squares world. And if you think about this in terms of growth modeling with categorical items, if u stars have been observed, for those of you who've done growth modeling, certainly in Mplus, you very often see that these epsilon variances are different across time. You don't have the same residual variance across time. It's often assumed to be the same, but typically if you test for it or look for it, let them be free, they are different. That then shows that you have a need for these so-called scale factors to not be the same fixed at 1 at all time points, but to be free for the second time point. Just giving you a little bit of a flavor for that. And finally then, as an alternative to maximum likelihood, we have the weighted least squares estimator. And I've been talking about it and talking about the weight matrix. It looks like, for those of you technically oriented, it looks like a walled statistic. S are the sample statistics. Sigma are the population counterparts coming out of the model. In this model on the left, you build the model not on tetrachoric correlations, but on Probit regressions, Probit thresholds, slopes, and residual correlations. Those are your sample statistics, which is a much weaker assumption of conditional normality for u star given x than full normality for u star and x, which you would assume if you use underlying latent correlations. And a full weight matrix is called GLS, generalized least squares. Mplus uses instead a diagonal weight matrix, which is easier to work with, much faster, and much more robust both statistically and computationally. That you can read about in my 1984 paper, if you're technically oriented, and even more technical, the paper together with Albert Sartora. And the latest developments along those lines, a simulation study in this Muthen specific paper, which is conditionally accepted to Psychometrica, but hasn't been revised yet, but is on my UCLA website, where you compare, when you do a simulation study to see what the sample size and needs are, and showing that this approach allows for good estimates and standard errors, even for samples as small as 200. That brings us to the last slide of the day. Just telling you that as we now say goodbye, and before we go to come back to Hopkins in August, we can have different levels of engagement. Just reminding myself to say that for licensed Mplus users, there is Mplus support. And yes, you do get support questions answered even on a Sunday morning. I don't know why, but. And for those, even for those of you who don't have a license on Mplus, you can use Mplus discussion for brief Mplus analysis questions of general interest. It's not for support. You should not post input and output and ask support questions. They won't be answered. And it's not for statistical consulting. That we can't take responsibility for that. We would have to know so much more, and it would take too much time. And in fact, statistical consulting is not available through Mplus. We wouldn't have time to develop the program if we got into that. It takes too much time. And actually, that is an interesting question. What do you do if you feel that you want to do some of these advanced analysis, but you don't feel totally that you master it? Well, the answer is you come back and learn more about it so you can do it yourself. Because those people who are really good at doing this, they're too busy to take on consulting. And those people who have time to do it, maybe they're not the right ones to ask. I don't know. I may be wrong. Here's an open field for anybody who wants to start up a consulting shop. There are lots of people who would love it. Now, there is the possibility, of course, also in exceptional cases, as research colleagues, you and I may want to interact on topics of common interest. Although I have to warn you, I'm pretty picky with the topic has to be closely related to the methods work that I'm doing, and the data have to be excellent, and you have to be a great substantive expert. But right now I'm working with half a dozen people across different places on topics of common interest. Right now, the interest of mine is randomized clinical trials regarding things like antidepressant medication, placebo response, and bad side effects. And I'm working with a psychiatrist at King's College London who's working on antipsychotic drug medication and different response classes in the growth mixture modeling arena, which is taking off in psychiatry quite a lot. And doing a little bit of work with Michael Sobel on causal modeling, which I'm trying to learn from him in the mediational area. Another level of engagement is you can find a good support group on SEMnet. SEMnet has traditionally, and still to this day, been a little too insulated, working only with continuous observed variables and the standard mean and covariance structure models. They're still lagging behind, but they're starting to open up to more flexible modeling. And if you start posting questions and answers here, the forum will become better, because there are people who are eager to learn and eager to comment. And I showed you this morning how to log on to how to get SEMnet communication. So with that, folks, you have the references, and apart from taking questions, we are done. Thanks. And Linda wants to thank you, too, for being such a good audience. And I'll carry forward the applause there to her. So let's see. Who wants to ask the first question? Who has energy left after all this? Particularly with that technical ending that I snuck in when Linda left church. Yes. Of the what variable? So the question is about having a 4-category variable with a strong, it sounds like a strong ceiling effect. And a person wants to do a multiple group analysis, factor analytic type of analysis. And the question is, when should she dichotomize the variable and just go on with the dichotomous variable? And there are a couple of points there. I would try to keep the information as much as you can and treat it as an ordinal categorical variable. And there are some exceptions to that. If you have a model with a lot of factors where maximum likelihood is hard to do, and you want to do weighted least squares, then you get into working with bivariate information. And if you have 4 categories with piling up at the high end, the pairs of variables, frequency tables, that you would use for these U-star correlation computations would be likely to have many zeros in them. Bivariate tables with many zeros can lead to problems with the weighted least squares approach. So in that case, that could be a reason why you want to dichotomize it. But in general, I would try to keep it as ordinal as long as possible, unless what I would tend to do is if you have a long tail where you have a high piling up, but you also have a long tail, some of those categories, if you have just 0.1 or 1% out here, some of those categories could be collapsed without losing too much information. Other questions? Yes.
On your slide 161 for interpretation, when you talked about males, we're given factor value, males have a lower probability of shoplifting. I'm just wondering, what factor, do you just focus on factor 1? Are you holding that constant? Or would you be also holding the other factor, the other 2 factors constant as well in the interpretation?
You don't have to, so the question is,
it's everything's being done simultaneously.
when you look at this direct effect, we only talked about conditioning on F1, and you don't have to condition on the other, F2 and F3, because they don't influence shoplifting. You know, there are no arrows from those. So in that case, you have a very simple case here. It's sufficient to condition on F1. But if you had cross-loading so that F2 also influenced shoplifting, then you would have to condition on F2 as well.
So technically, you could have done a simple factor analysis, just dealing with those F1 variables.
You could, yes.
Would you have gotten a similar answer?
You would have, if you had just 6 and these 8 property offense items, you would most likely get very similar answers, yes. Yeah. In the back.
Could you comment briefly on the 2 parameterizations for the categorical models?
The IRT and the Mplus?
No, I'm sorry, the delta and the, I can't remember which one.
Oh, delta and theta, okay.
Just when it's appropriate to use the 2.
Yeah, so the question is, in the weighted least squares setting, you have a choice of parameterization, a so-called theta and a so-called delta parameterization. What we talked about, and what is the default in most cases, is the delta approximation. Delta approach, delta parameterization. Delta standing for these scale factors. Again, delta being the inverted standard deviation of the residual U-star variance, which we would like to allow to vary across time. The theta parameterization, instead of working with those scale factors, work directly with the residual variances of the epsilons here. Some find that more intuitive, more in line with continuous items, if the U-stars are being continuous. And the theta parameterization then would fix the variance for the epsilon to 1 at the first time point, but let them be free and therefore different at the other time points. And you would think that why not always use the theta parameterization? That seems so intuitive. Well, it turns out that this web note 4 shows that that theta parameterization can run into trouble in certain situations where the delta approach doesn't. And that can occur in multiple group settings, in longitudinal settings, but also in path analytic settings. For instance, you have to use the theta parameterization. Well, and the opposite case is you have to use the theta parameterization when a categorical variable is in the middle of a chain, is influenced by a categorical variable and influences categorical variable. if you try to do the delta parameterization, Mplus will tell you this particular path model needs a theta parameterization. So that's quite high level stuff, but it is described in the user's guide, and Mplus gives pretty good messages about what you need to do there. Yes.
In mimic model, you said that after you add the direct effect, you gotta check the measurement structure, whether it changes or not. So in practical ways, that means that you gotta check whether the vector loading is different before and after.
Yeah, so the question is, we said that we should, when we include direct effects, we should check that the measurement structure stays the same. And that implies the loading for shoplifting and for the others, and the thresholds for the others shouldn't jump around a lot. If it does, then, well, I guess it's an indication then that direct effects are really needed. And you also want to keep a tab on whether or not the structural effect of sex on F1 changes. But the model that you would, if there are big differences, this model with direct effect would be the one that's more trustworthy. Yes, other questions? You are energetic, folks. Okay.
For slide 150, please.
150?
Yes. Assuming I have one of the variables, the dependent variables is nominal, can I regress that nominal variable on one of the latent factors, like let's say F1 or F2, by just saying X, it being nominal on F1, in this case, in this graph?
So the question is here about a nominal variable being a dependent variable as a function of a latent continuous variable.
Right.
And that's one of the cases that we don't cover at this point. So, because it gets into a different kind of modeling framework.
And it's asking for a lot of numerical integration points. So I guess that's the error that I'm getting.
Okay, yeah. It's, that's related to discrete choice models. And, you know, it's a little bit different of a situation than these. But if we have a lot of emails about that, there are possibilities to do something about that. For instance, Darrell Bach has a great multivariate book. And I still remember his chapter 8 talking about these discrete choice models, where you basically have a latent response variable for each of the nominal categories. And the model says the person chooses the nominal U category corresponding to the highest peak of those U-star distributions. But it's one U-star distribution for each response category.
So at this point, sorry.
Yeah, a little bit different animal.
So at this point, if I should probably keep them binary, right? Work with dichotomies.
Right.
Okay, thank you.
Okay, other questions? Yes, one more. Boy.
With the multiple group analysis, like for example, slide 169, it's relatively simple if you have one covariate. You do the model, you do the model, and the model. Can you do a multiple group analysis with multiple covariates, like using sex and black and age? And if so, how would you set that?
Yeah. So the question is, can you have a multiple group model where the groups are defined by several variables? And yes, I think that 89 Psychometrica paper that had did that. You just create a combination variable, a dummy variable that combines them. And then you can have gender by ethnicity by age groups and get all those possible cells corresponding to the groups. And that would then say that if you get a significant difference, you may then want to go in and try to test which aspects, which grouping variables cause the difference. And you can do tests of that using the model test feature, ad hoc, post hoc, not ad hoc, but post hoc tests. But that's quite possible. The problem is when you don't have large enough samples to have enough people in each group, particularly when you analyze rare events, which we often have when we work with categorical outcomes. All right, one more question, and then we have to wrap up here, I think.
So what is the bare minimum requirement of sample size per group in that case?
What's the bare minimum sample size when you have multiple groups in categorical outcomes? My chapter in that Eaton et al. Article from '89 talks about that a little bit. It's totally dependent on how rare the U event is. So it's and other model parameters. I think that's a good candidate for a simulation study to really be able to say. The rules of thumb would be much too crude for any given application, I would think. But certainly the sample size requirements go up quite a lot when you do that. All right, folks.